This video is on real numbers from Exemplar. In this video, I am going to explain first 5 sums of exercise 1.2. This is my part 3. Now exercise 1.2. Now the first question is, write whether every positive integer can be of the form 4q plus 2, where q is an integer. Justify your answer. I am to explain whether this statement is right or wrong. Now I'm going to write Euclid division lemma here. Given two positive integers a and b, here b is equal to 4, there exist unique integers q and r such that a is equal to 4q plus r lies between 0 to 4. It means r can be 0, 1, 2, 3. If r is equal to 0, so a is equal to 4q. If r is equal to 1, a is equal to 4q plus 1. If r is equal to 2, a is equal to 4q plus 2. If r is equal to 3, a is equal to 4q plus 3. It means every positive integer is of the form 4q, 4q plus 1, 4q plus 2, and 4q plus 3. Here in the statement, it says every positive integer can be of the form 4q plus 2, where q is an integer. No, this statement is wrong. It should be every positive integer should be of the form 4q, 4q plus 1, 4q plus 2, 4q plus 3. Now the second sum is, now the question is, the product of two consecutive positive integers is divisible by 2. Is this statement true or false? Give reason. First of all, I am going to explain what are two consecutive positive integers, like 2, 3, 14, 15, 21, 22. They are two consecutive positive integers. In general form, we write it as n plus 1. They are two consecutive positive integers. What you have seen, here one number is even, the other number is odd. When we write consecutive positive integers, one number is always even. See, here 2 is even, here 14 is even, here 22 is even. If I write another number 35, 36, here 36 is even. So one number must be even and the other will be odd. And if one number is even, it will be divisible by 2. Similarly, it means n plus 1. One number must be even, either n or n plus 1. One number must be even, so it will be divisible by 2. So this is a true statement. The product of two consecutive positive integer is always divisible by 2. So this is a true statement, because consecutive integers can be written in the form of n plus 1. And 1 out of n or n plus 1 must be even. That is why product of two consecutive positive integer is divisible by 2. So this is a true statement. Now the third question is, the product of three consecutive positive integers is divisible by 6. Is this statement true or false? Justify your answer. Now, what are the three consecutive positive integers? Now in the question, the product of three consecutive positive integers is divisible by 6. So first I'm going to write three consecutive positive integers, and then I'm going to write their product, and then I'll see whether they are divisible by 6 or not. So 2 into 3 into 4. They are three consecutive positive integers, but I have seen they are divisible by 2 and they are divisible by 3. Now let me write one more. 11 into 12 into 13. Now this number is divisible by 2, this number is divisible by 3. It means this is divisible by 6. Write one more. 31 into 32 into 33. Now this number is divisible by 3. This number is divisible by 2. It means this is divisible by 6. So what we have seen, this is divisible by 6, this is divisible by 6, this is divisible by 6. So product of three consecutive positive integer is divisible by 6. So this is a true statement. So this is a true statement. How you will do it in the exam? Three consecutive positive integers can be written in the form of n plus 1, n plus 2. So if we generalize it, so what we are going to write? Three consecutive positive integers can be written in the form of n plus 1, n plus 2. So the product of n plus 1, n plus 2 will always be divisible by 6, because at least one of the factors will be divisible by 2 and at least one of the factors will be divisible by 3. So this is a true statement. Now the fourth question is, write whether the square of any positive integer can be of the form 3m plus 2, where m is a natural number. Justify your answer. Now the question is, I am to check whether square of any positive integer is of the form 3m plus 2. Now its answer is no. Explain why the answer is no. Now I'm going to write Euclid division lemma for two positive integers a and b, where b is equal to 3. Let a and b, where b is equal to 3, are two positive integers. Then there exist two positive integers q and r such that a is equal to 3q plus r lies between 0 and 3. Then r is equal to, value of r will be 0, 1 and 2. If r is 0, a is equal to 3q. If r is 1, a is equal to 3q plus 1. If r is 2, a is equal to 3q plus 2. Now, any positive integer can be written in the form of 3q, 3q plus 1, 3q plus 2. Now, I'm going to find the square of it. Now, square of 3q whole square is equal to 9q square. That is 3q square. It can be written like this. And this is equal to 3m, where m is a positive integer. Now, if I take 3q plus 1 whole square, this is equal to 3q whole square plus 2 times into 3q plus 1 whole square. That is equal to 9q square plus 6q plus 1. Take 3 common from this. You will have 3q square plus 2q plus 1. This is equal to 3m plus 1, where m is positive integer. Now find 3q plus 2 whole square. It is equal to 3q whole square plus 2 times 3q into 2 plus 2 whole square. This is equal to 9q square, 12q plus 4. This can be written as 9q square plus 12q plus 3 plus 1. Bifurcate 4 as 3 plus 1. Take 3 common, you will have 3q square plus 4q plus 1 plus 1. This is equal to 3m plus 1, where m is a positive integer. It shows square of any positive integer is of the form 3m and 3m plus 1. So in the statement, he says square of any positive integer can be of the form 3m plus 2. No, the square of any positive integer is of the form 3m or 3m plus 1, not 3m plus 2. So this is a false statement. Now the fifth question is, a positive integer is of the form 3q plus 1, q being a natural number. Can you write its square in any form other than 3m plus 1? That is, 3m or 3m plus 2 for some integer m. Justify your answer. He says, can you write its square in any form other than 3m plus 1? Can you write it in the form of 3m or 3m plus 2? Now let us check it, whether it is of the form 3m plus 1 or whether we can write it in the form of 3m or 3m plus 2. So let us check it, square it. 3q plus 1 whole square. 3q plus 1 whole square. This is equal to 3q square plus 2 times 3q into 1 plus 1 whole square. That is equal to 9q square plus 6q plus 1. That is equal to, take 3 common, you will have 3q square plus 2q plus 1. So instead of 3q square plus 2q, I have written m, and where m is a natural number. So what we have seen, square of a positive integer 3q plus 1 is of the form 3m plus 1. We can't write it in the form of 3m or 3m plus 2. When he says, can you write its square in any form other than 3m plus 1? No, we can't write its square in any form other than 3m plus 1. So answer is no. We cannot write square of positive integers 3q plus 1 in any form other than 3m plus 1. So in this video, I have explained first 5 sums of exercise 1.2 of Exemplar. In the next video, part 4, I am going to explain next 5 sums from 6 to 10 of exercise 1.2 of Exemplar.